Hi there. Welcome to a series of videos that I'm hoping to make where I solve various AP calculus problems. This will hopefully save time in the classroom and allow us to go on with new material. If you ever have any questions about the AP problems that are assigned for homework, you can hopefully come to one of these videos and check it out. So the one we're going to do today is 2014 problem number 3. It's got a bunch of parts, so let's get started. So to set up the problem is this. We have this function f of x, which is defined from -5 all the way up to 4. This point right here is -4, comma -4. It's a continuous function. You can see that it's a piecewise function. It's made up of 3 lines. There's a tendency as a student to want to therefore try to write f of x down as some piecewise defined function, where you figure out what each one of these lines are and you do this. I would not recommend doing this. Usually there's a better way to do the problem. Okay, so that's the basic setup. Then we have this other function g of x, which is defined as the definite integral of f starting at -3 and going all the way up to x. So the point of g of x is that it is the accumulation function for f of x. It tells us how the area under f of x is accumulating starting with -3. Now I should put area in quotes here. It's not really an area, it's what we call a signed area, because remember, for the definite integral, if you're going forward and the function is above the x-axis, the area is considered positive. If it's below, it's considered negative, and then the opposite of that is true if we're going backwards. Now, I would like to make a real quick aside. One of the things that always bothered me when I was first student learning calculus, I had a really hard time with this t appearing here. I didn't understand why that was necessary. Well, let me show you why. The idea here is that g is actually a function of x. And if we were to go ahead and throw an x all through here and say that g of x equals the integral from -3 to x of f of x dx, if we were to say this, then what would g of 3 be? Which, by the way, is what we're going to be asked to compute in part A. Then g of 3, the way we plug in the value for x is wherever we see an x, we replace it with a 3, so we would get the integral from -3 to 3, so far no problem, of f of 3, that's just a number. So we're finding the area, and we're not finding the area under f of x, we're finding the area under f of 3 under a constant. But it's even worse than that. d3 question mark? What the heck does that mean? It doesn't mean anything. That's why we can't do that. And so what we end up having to do is creating what we call a dummy variable, t. You can actually call it anything you want, but it's pretty standard to use a t. Okay, so let's get started on the problem here. The first thing we're asked to do in part A is compute g of 3. So let's see. G of 3, using this formula down here, is the integral from -3 to 3 of f of t dt. And I should point out that now that the 3 is completely gone, there's nothing wrong with us simply writing this as the integral from -3 to 3 of f of x dx. These are literally equal to one another. This means the area, signed area under f from -3 to 3, using the variable t as your independent variable. Here you're using the variable x. Doesn't actually matter. So if this really bothers you, you can pick one or the other. I'm going to stick with the t because I don't really care. I suppose, given that I'm sticking with the t though, this is then sort of the t-axis. Okay, so we're being asked to find the area under f from -3 all the way up to 3. Okay, so -3 starts right here. And so we've got this area. That seems pretty easy. That's just a triangle. All the way up to 3, which is right here, and that area. So we're going to have one positive area, one negative area. Now the positive area is actually easy to compute. This is just a triangle. So we're going to do 1/2 base times height. So let's see here, I'll put it in red. So we have 1/2 the base. So this distance right here is 1, 2, 3, 4, 5. That's the base. And then the height, 1, 2, 3, 4. Okay. plus the area of the triangle. Now this one's going to be negative, so I could have written minus, but we're adding these two. Now this one, my picture here is drawn pretty well to scale, and if you wanted to, you could probably realize, and the picture on the actual paper is even better, you probably realize that this point right here is 3 comma negative 2. But you can actually check that. It's not very hard to do so, and it turns out it'll be useful later on in the problem. So looking at this line right here, we can check this. We can actually find the equation of this line. Now I said we don't want to find the equations of all of them, but I think this one's necessary. I'm not even actually really positive that it crosses there at 2, and it would probably be a good idea to check. So here we go. Actually, I think I am positive it crosses there at 2. So let's see. The cool thing about this line is we actually know the y-intercept already. So we can just use y equals mx plus b form. So what's the slope? Well, the rise is negative 4, and the run is 2. So the equation of this line is y equals rise over run, negative 4 over 2, negative 2x plus, and then it crosses at 4. So y of 3, which is what we're trying to find out now, y of 3 is negative 2 times 3 plus 4, which is in fact negative 2, like we thought. So, therefore, the area of this triangle is 1/2 base. The base here is 1, and then the height here is 2. So 1/2 base times height. Altogether, if you do the arithmetic here, you're going to get 10 minus 1, which is 9. Perfect. So that is the first part of the problem. Okay, so now on to part B. Part B asks, when is g of x increasing and concave down? So these concepts, increasing and concave down, are concepts about the graph of g. They talk about the shape. Increasing means that the shape, as you go left to right, the shape of the function is that it's going up. Concave down means that has something to do with like the curvature of how it's going. We want it to be going up, but we want it to be doing so unhappily, is how I like to say it, kind of going down up like this. Now, unfortunately, we do not have the graph of g. We have the graph of f, and it is tempting to try to answer these questions using f, but we have to be very careful not to do so. Unfortunately, we do not have the graph of f, or the graph of g. The graph of g is something totally different. Now, I could try to draw the graph of g, but it would be a bit of a waste of time. I think there's a faster way to do this. So, if we're interested, it has to do with how the derivatives of a function relate to the shape of a function. So you might remember the sine of g prime, the sine of the derivative of g, is related to the increasing, decreasing behavior of g. If g prime is positive, then g is increasing. The graph of g is increasing. So here's what we need. We need g prime of x to be positive. This gives us the increasing part. And the second derivative's job, the sine of the second derivative, tells us about the concavity of the function. So we need g double prime of x to be negative. This gives us the concave down part. Okay, but what the heck is g prime? This is g. What's g prime? Well, the big idea here, this is the fundamental theorem of calculus part 2. Turns out g prime of x is in fact just f of x. This thing we're looking at right here. Note also that the t has disappeared. This is another thing that often scared me. We got this f of t going on, but g prime of x is indeed a function of x, not of t. T isn't really here. It's a dummy variable. In fact, if you think about the fundamental theorem of calculus part 1, the way you would compute this integral is you take the antiderivative of little f, and then you'd plug in x and negative 3 and subtract them. The t's would disappear. You'd be left only with x's. So g prime of x is a function of x, and g double prime of x is f prime of x. So here we go. We need f of x to be positive. Well, here's the graph of f. In order for f to be positive, this means that f is above the x-axis. Now, I say positive, but really I'm also going to allow 0 as long as it's at specific places. So when the derivative of a function equals 0, it's flat. It's not technically increasing or decreasing at that place, it's flat. But it's a subtle point, and I don't think they actually care very much about this. So what I'm about to say isn't totally correct, but f is above the x-axis all the way starting at -5 and going up to 2, it looks like. -5 to 2. Again, technically at -3 it's 0, and at 2 it's also 0. So let's just put a little, so I'm not saying something false, let's put a greater than or equal here. Here I need this to be less than or equal to 0. Well, the derivative of f is the slope of the tangent line to f. And in fact, the tangent line of f, it has 3 different tangent lines. One here, and one here. And 2 of them have a negative slope. So right here, this one has a negative slope from -5 to -3. Well, and also from 0 to 4. Now, of course, we want both of these things to be true at the same time. So let's see, when do these things happen at the same time? It looks like we have it happening right here and right here. Those are the 2 places where this is happening. So my final answer, therefore, is, I'm going to go ahead and erase this. The final answer right here is from -5 to -3, and from 0 to 2. Beautiful. All right, so that is part B. Let's move on to part C. Part C. In part C, we define a new function. We define this function h of x, which is equal to g of x over 5x. And they want us to compute, find h prime of 3. So what is this problem all about? Yeah, this problem is about the quotient rule. And again, a little bit of the fundamental theorem of calculus part 2. So h prime of x, we have to use the quotient rule, is low d high g prime of x minus high d low. Derivative of 5x is just 5, all over low. And now we plug in h prime of 3, and it equals 15 times g prime of 3 minus g of 3 times 5 over 15 squared. So what's g prime of 3? Well, if you remember, g prime of x is just f of x. Remember, this is just f of x. So in fact, this is just 15 times f of 3 minus g of 3, but we figured out what g of 3 was in the last problem. G of 3 is 9. This is from part A. Times 5, all over 15 squared. Now we still have to figure out what f of 3 is, but that's not so bad. Flip the board over here, and we can look at the graph of that, which we totally have. And it looks like f of 3, oh yeah, that's -2. That's the thing we checked when we found that line. So it's -2. So we have -2, so that's going to be, this right here is -2. So we end up having -30 minus 45 over 15 squared. This is -75 over 225, which I think is -1/3. I should point out that for the purposes of the AP exam, you don't have to do a lot of this simplification. If you kind of stopped probably right here, you would be good. You certainly don't have to get to -1/3. Okay, so that's part C. Part D does something similar. So part D, we defined a new function, p of x, which is f of x squared minus x. And we're asked to find the slope of the tangent line to p at -1. So we want find the slope of the tangent line to p, that's the derivative of p. So we want p prime of -1. All right, so what is this problem about? This problem is about the chain rule. So here we go. Let's see, we're going to find p prime of x generally. P prime of x is f prime of x squared minus x times the derivative of the inside, 2x minus 1. Therefore, p prime of -1 is f prime of, let's see, -1 squared minus -1 times 2 times -1 minus 1. Cleaning all this up, it looks like this is f prime of, that's going to be 1 minus -1, 2, times 2 times -1 is -2 minus 1 is -3. So it looks like we need to know f prime of 2, but guess what? That's also something we figured out in part A. F prime of 2 is the slope of this line, which I believe we found from part A was -2. Rises -4, runs 2. So this is -2. And here we go. This ends up being -2 times -3, which is 6. And that completes this problem.